Digital control systems can be designed in a variety of ways to meet the needs of various process systems. The design of a particular control system depends on the process to be controlled and on the type of control needed. For example, the requirements of a sequential process system, in which operations occur one step at a time, may be very different from the requirements of a continuous process system, which may involve many more process variables and which may require complex types and modes of control. A programmable controller is a computer-based process control device. Programmable controllers are commonly used to establish protective circuits, such as safety interlocks, and to control operations in sequential process systems. When programmable controllers are used in these and other applications, the control logic that determines the actions taken and their sequence is easily programmed into the controller. The programming consists of a set of instructions called a control logic program. When a programmable controller is running, it performs a sequence of activities that's called a scan cycle. A scan cycle is executed many times a second. This illustration shows three process control activities that typically take place during a scan cycle. The first activity that the programmable controller performs during the scan cycle is reading all of its inputs and storing their values in memory. After that, the programmable controller evaluates its entire control logic program. Based on this evaluation, it updates values that are in output memory locations. Finally, the programmable controller uses the values in the output memory locations to generate output signals that control process equipment. A programmable controller can operate either on its own or with other control devices in a process control system. In addition to its process control capabilities, a programmable controller has communication capabilities that it can use to transfer data to and from other devices over a communication network. Process equipment is often protected by safety interlock systems. A safety interlock system prevents a piece of equipment from operating unless a predetermined set of conditions exists. Programmable controllers are typically used to establish safety interlock systems that are based on the use of two-position devices such as switches. In this type of system, the programmable controller detects the position of each switch, uses that information while evaluating its control logic program, and then sends a signal to the process controller that controls a specific piece of process equipment. This signal informs the process controller whether or not the equipment can be operated safely. For example, here's a simplified illustration of a safety interlock system that's associated with a pump. A lube oil system provides the pump with lubricating oil. A process controller automatically controls the operation of the pump by starting and stopping the pump's motor as needed. An operator can also use the process controller to start and stop the motor manually. In order for the pump in this example to operate safely and efficiently, three conditions must be met. The inlet valve in the fluid line must be fully open to provide fluid to the pump. Lube oil pressure to the pump must be sufficient, and the flow of lube oil to the pump must be adequate. To ensure that these three conditions are met before the pump is started and while it's operating, the states of three process variables, fluid flow, lube oil pressure, and lube oil flow, are monitored. A limit switch in the inlet valve assembly is energized when the valve is fully open. When lube oil pressure reaches a predetermined value, this pressure switch is energized. And when lube oil flow reaches a predetermined value, this flow switch is energized. When any of the three switches is energized, that switch's signal is sent to the system's programmable controller. The programmable controller reads the signals it receives and evaluates its control logic program using these inputs. If any of the three conditions is not met, the pump cannot be started. For example, if the lube oil pressure is too low, its switch will not send a signal to the programmable controller. As a result, no signal is sent to the process controller, so the pump cannot be started. However, if all three of the conditions are met, the programmable controller sends a signal to the process controller. The process controller can then start the pump. Once the pump is running, the programmable controller continues to check the three inputs to make sure the three conditions are still being met. If one or more conditions change during operation, and the programmable controller does not continue to receive signals from all three switches, the programmable controller would not send a signal to the process controller, so the process controller would automatically shut down the pump. The pump in this example is protected by an interlock system. Unless all three required conditions are met at all times, the safety interlock system either prevents the pump from being started or shuts it down to prevent equipment damage. Programmable controllers are often used with terminals that have display screens which operators can use while working with the system. For example, in a safety interlock system, a terminal's display screen can show the arrangements of the interlocks. When a problem occurs, an operator can use the terminal to determine exactly which interlock is affected. This saves the operator time in identifying and correcting the problem. Sequential process system operations occur in sequence, that is, one step at a time. Since this is also how a control logic program is evaluated, a programmable controller is ideally suited to be the controlling element in a sequential process system. This is a simplified illustration of part of a process system that is operated sequentially. In this part of the system, two fluids are mixed in a tank, and then the mixture is sent on for further processing. When the system is not operating, these two fluid inlet valves and the product outlet valve are all closed, and the mixer's agitator motor is shut off. When the programmable controller is started, the system begins operation. During operation, the programmable controller reads input signals from these two level switches. Then it evaluates its control logic program and sends signals to the valves and the agitator motor. To begin, the programmable controller opens the lower inlet valve to start the flow of the first fluid into the mixing tank. When the level of the fluid reaches the lower level switch, LS1, that switch is energized. The programmable controller reads the signal coming from LS1. After reading the signal from LS1, the programmable controller uses the information to close the lower inlet valve. According to the programmable controller's control logic program, after the lower inlet valve is closed, the programmable controller sends a signal to the agitator's motor, which starts the mixing action. Next, the programmable controller sends a signal to the upper fluid inlet valve. That valve opens, allowing the second fluid to enter the tank. When the level of the mixture in the tank reaches the upper level switch, LS2, that switch is energized. The programmable controller then reads the signal coming from LS2. After reading the signal, the programmable controller uses the information to close the upper inlet valve. The two fluids continue being mixed by the agitator for a period of time that's been programmed into the control logic program. After the mixing period has elapsed, the programmable controller turns off the agitator's motor. Then the programmable controller sends a signal that opens the product outlet valve. The fluid mixture leaves the tank through the outlet line and is sent on for further processing. The operation of the system in this example is sequential. When one step is completed, another step begins. The programmable controller ensures that the proper preceding step has been completed before starting the next step. For instance, in our example, the agitator's motor must be turned off before the outlet valve is opened. If the valve is opened before the fluids are properly mixed by the agitator, the resulting product might not meet plant specifications. In this topic, we went over the fundamentals of programmable controllers. We also looked at two common applications of programmable controllers: interlock systems and sequential operations. Now's a good time to try a few practice questions. When a programmable controller is running, it performs a sequence of activities that's called a scan cycle. A scan cycle is executed many times a second. Sequential process system operations occur in sequence, that is, one step at a time. Since this is also how a control logic program is evaluated, a programmable controller is ideally suited to be the controlling element in a sequential process system. There are several different types of process unit digital control systems. The differences between them are mainly in how the control function in each system is arranged. In one type of system, the control function is centralized. This means that all of the process control functions in the system are performed in a single location. This type of control is commonly called direct digital control, or DDC. The main component in this type of control system is a DDC computer. This one has a built-in control panel and display screen. A DDC computer directly inputs and outputs data that it needs to control all of the control loops in the process. Generally speaking, a DDC system works like this. Input signals are sent from the process to the computer, which stores their values in memory. Each input value is compared to the appropriate set point value to determine a corresponding output value. The computer uses the output values to generate output signals. These signals are sent directly to control devices that adjust parameters within the process to keep it under control. A second type of process unit digital control system is called a distributed control system, or DCS. A distributed control system is a system in which control of a process is divided among and coordinated between various control units. A DCS uses numerous digital controllers to control different parts of a process. These controllers can act independently. However, to achieve total process control, the controllers need information from outside sources, such as operator consoles and other digital controllers. The interaction between devices in a DCS is made possible by the use of a communication network. Although there are several different types of distributed control systems, they have some similar major components. For instance, in addition to the controllers we just talked about, there are operator consoles. Operator consoles have keyboards that allow operators to send commands and data to the rest of the system. They also have displays that give operators information about the system. Network equipment, such as this traffic director, manages the flow of data on the system's communication network. Memory devices supplement the memory capacity of the computers and the process controllers. And communication interfaces connect the equipment in the system to the network. During operation, each controller in a DCS controls its part of the process. The controllers use the communication network to transfer data to and from other controllers and other devices connected to the system. Operators usually monitor and direct process activities from an operator console, where they have access to all of the other devices in the system through the communication network. A supervisory control system is a system in which a supervisory computer directs the activities of many process controllers. The process controllers can be any combination of digital controllers and analog controllers. A major characteristic of supervisory control systems is that the supervisory computer does not directly control the values of process variables. Instead, it directs the activities of the process controllers in the system. Normally, the supervisory computer determines set points based on measurements of process variables sent to it by the process controllers. The process controllers then generate corrective actions based on the difference between the measured values of the process variables and the computer-generated set points. Supervisory computers are also able to evaluate information about actual operating conditions in the entire facility. By evaluating information from the entire facility, the computer can efficiently allocate resources in the facility. Examples of facility-wide information include the costs of raw materials, the values of products, and current process variable values. In addition, supervisory computers optimize the operation of units under their control. In this context, Optimizing means using more complex control logic, which enhances system performance to improve efficiency and coordinate activities. Supervisory computers also collect and maintain information, such as inventory and energy usage, and they perform diagnostics on themselves and on process-connected control equipment. In this topic, we saw how centralized digital control systems and distributed control systems can be used to control continuous process systems. We also looked at supervisory control systems. Now take the time to try a couple of practice questions on this material. There are several different types of process unit digital control systems. The differences between them are mainly in how the control function in each system is arranged. A major characteristic of supervisory control systems is that the supervisory computer does not directly control the values of process variables. Instead, it directs the activities of the process controllers in the system.